A vector is a column of real numbers. The set of all vectors with n entries is called Rn. We draw a vector as an arrow from the origin, moving along the axes as specified by the coordinates. We can also draw this arrow starting from a different point and consider it to be the same vector. The length of a vector is the length of its arrow. The fundamental vector space operations are addition of two vectors and multiplication of a real number, also known as a scalar in this context, and a vector. A linear combination of a list of vectors is a sum of scalar multiples of those vectors. The scalars are called the weights of the linear combination. The span of a list of vectors is the set of all vectors that can be written as a linear combination of those vectors. For example, the span of two non-collinear vectors in 3D space is a plane. A list of vectors is linearly independent if none of the vectors is in the span of the others. A vector space is a set of vectors which is closed under the vector space operations. The first quadrant is not a vector space because it's possible to multiply a vector in that set by a scalar, namely -1, and get a vector which is not in that set. A linearly independent list which spans a vector space V is called a basis of V. The number of vectors in a basis of V is called the dimension of V. Any linearly independent list can be extended to form a basis, and any spanning list can be trimmed to form a basis. A transformation T is linear if it respects the vector space operations. For example, a rotation about the origin is linear. Other examples of linear transformations include scalings, projections, reflections, and shear transformations. Linear transformations can be represented using matrices, which store the coefficients in the formulas for the entries of t of x1 up to xn. We define the product of a matrix and a vector so that applying a transformation is the same as multiplying by its matrix. Equivalently, a matrix times a vector is equal to the linear combination of the columns of the matrix whose weights are the entries of the vector. We define the product of two matrices so that products are associative. The result of this definition is that the ijth entry of the product AB is equal to the result of multiplying corresponding entries of the ith row of A and the jth column of B and summing the results. Another handy feature of matrix multiplication is that we can slice up matrices into blocks and multiply those blocks as though they were numbers. A linear transformation is fully specified by the images of the vectors in a basis. The rank of a transformation is the dimension of its range. The nullity of a transformation is the dimension of the space of vectors that maps to the zero vector. The rank nullity theorem says that the rank plus the nullity of a transformation equals the dimension of its domain. At one extreme, a transformation can map only the zero vector to the zero vector and have rank equal to its domain's dimension. From there, to shrink the dimension of the range by 1, we have to map an extra dimension's worth of vectors to 0. A linear system of equations can be represented as a matrix equation. We can interpret this equation in vector terms. What linear combination of the columns of A is equal to B? From this point of view, we can draw several conclusions about the equation AX equals B. AX equals B has a unique solution only if the columns of A are linearly independent. And AX equals B has either no solution or infinitely many solutions if A has more columns than rows. This is because the columns are in Rm and there are more than m of them. Therefore, they're necessarily linearly dependent. If a square matrix is invertible as a map from Rn to Rn, then its inverse is linear. If A and B are square with the same dimension, then the inverse of the product AB is equal to the product of the inverses B inverse and A inverse. The transpose of a matrix is obtained by swapping rows and columns. Like taking the inverse, taking the transpose distributes across multiplication but reverses the order. The dot product of two vectors measures their alignment. For two vectors of a fixed length, their dot product is maximized when the angle between them is 0, and it's minimized when the angle between them is 180 degrees. In between, the dot product is 0 if the two vectors are perpendicular. The dot product can be written as a matrix product by replacing the first vector with its transpose. And the dot product of a vector with itself is the squared length of that vector. To find the component of a vector A in the direction of a unit vector u, we dot A with u. A list of vectors is orthogonal if each pair of vectors in the list is orthogonal. If, in addition, every vector in the list has unit length, we call the list orthonormal. This matrix U has orthonormal columns. Equivalently, a matrix with orthonormal columns satisfies U transpose U equals the identity. A matrix with orthonormal columns which is also square is called an orthogonal matrix. Matrices with orthonormal columns preserve length, so you can think of them geometrically as rotations. The action of a matrix like 3, 0, 0, 2 is easy to understand because we can think of it as scaling along the x-axis followed by scaling along the y-axis. Then we can say that the inverse of this matrix is the matrix which scales by a factor of 1/3 along the x-axis and a factor of 1/2 along the y-axis. We can also find a matrix that squares to give this matrix, namely the one with diagonal entries √3 and √2. Both of these problems are less straightforward for general matrices. Those handy off-diagonal zeros arise from A preserving the direction of vectors which run horizontally or vertically. Vectors with this property are called eigenvectors, and if we can find a basis of eigenvectors of a matrix A, we can reason about A as effectively as we can reason about a diagonal matrix like 3, 0, 0, 2. We say that a non-zero vector V is an eigenvector of A if AV has the same direction as V. In other words, if AV equals lambda V for some scalar lambda, which we call an eigenvalue. For example, this matrix multiplied by 1, 1 is 2, 2. So 1, 1 is an eigenvector with eigenvalue 2. Likewise, minus 1, 1 is an eigenvector with eigenvalue 3. Since these vectors form a basis of R2, we can write any vector as a linear combination of these vectors. Representing V in this way, we can see that applying A to V doubles the C1 value and triples the C2 value. Not every matrix has a basis of eigenvectors. A 2x2 rotation matrix, for example, turns every vector, so it doesn't preserve the direction of any vector. Some matrices don't have enough linearly independent eigenvectors. For example, 1, 2, 0, 1 preserves 1, 0, but it turns every vector which does not run horizontally. A matrix which does have a basis of eigenvectors is called diagonalizable. Diagonalizing an n by n matrix means writing it in the form V lambda V inverse, where V is an n by n matrix whose columns contain linearly independent eigenvectors of A, and where lambda is a diagonal matrix containing the eigenvalues on its diagonal. The equation A equals V lambda V inverse holds since it's equivalent to AV equals V lambda, and that equation unpacks using the definition of matrix multiplication to the eigenvector equation in each column. As an application of eigenvectors, let's consider the Fibonacci sequence. The map which takes us from a pair of terms to the pair 1, over is linear, and its matrix is 0, 1, 1, 1. Therefore, the nth term of the Fibonacci sequence is equal to the top entry of a to the n times 0, 1. Since we can raise a diagonal matrix to a power by raising each diagonal entry to that power, let's look to diagonalize this matrix A. We want to find values of lambda so that the equation AV equals lambda V has non-zero solutions. This is true if and only if A minus lambda times the identity maps some non-zero vector to 0. In other words, we want to find lambda so that A minus lambda I is not full rank. Since this matrix only has 2 columns, they are linearly dependent only if one is a multiple of the other. The solutions of this equation are 1 plus or minus square root 5 all over 2, which can also be written as phi and 1 minus phi, where phi is the golden ratio. Substituting back into the eigenvector equation, we find eigenvectors of 1 phi and 1 minus phi. We can write the starting vector 0, 1 as a linear combination of these two eigenvectors, with weights 1 over square root 5 and minus 1 over square root 5. Therefore, the nth Fibonacci number has a formula in terms of n and the golden ratio phi.